right, so speaking of, so let's get back to this here. Do not solve it. Don't solve it. Just find these 8 things. Find your, so the confidence level is like, okay, so everyone look up, confidence level means like 95% interval, 90% interval, 99% interval, whatever it is. And then remember, alpha is the opposite of the confidence level. 95% confidence level means alpha is 5%. It's the rest of it, right? And then this is just alpha divided by 2. So find those 8 things, and we'll go over them in just a minute or two. Let's take a look. What's my sigma? What's my standard deviation?
29.6.
29.6. What's my confidence level? 9%. So it means my alpha is 1%, right? Typically we write alpha as a decimal and confidence level as a percentage. How it is, alpha over 2 is half of 0.01, which is 0.005. And if you did inverse over 0.005, you would get 575. Yep. Okay, great. Now, so go look at the top part. What's my n? Yes, sample of. Sample of is your n. Now it gets a little bit tricky. So my average, my mean is my average, right? Here's the deal. Is this from the sample or from the population? Well, here's the second thing. What are we trying to find when we find a confidence interval? What are we trying to estimate when we estimate a confidence interval? The population mean. So the population mean isn't given, it's what we're trying to find. So we don't know it. We're trying to estimate it. So this is a little bit tricky. I want to make sure everybody understood that this is what we don't know the population mean. We don't know. This is what we're trying to find.
Interesting.
And I put that in there on purpose so that you folks will realize that's what a confidence interval is. We're trying to estimate our population mean or our population proportion. This being a mean problem, it's going to be a population mean. So the first part says averages 362 customers. A random sample of 40 was used to determine the average. So that average came from a sample of 40. So that means that that's our sample mean. Does everybody see that part? Right? A sample of 40 hours was used to determine the average. So this is 362. Good? All right. Perfect. So we'll take a look. Here's the problem people wanted for home. We're gonna skip it. So let's move down to the next thing. Here's the deal. This is all estimating population mean based upon using the standard deviation, the population standard deviation. How often do you think in real life do we not know the population mean, but we do know the population standard deviation? Very often you use the mean to find the standard deviation. So how can I know one without knowing the other one? In real life, that rarely ever happens. So the first year and a half I taught this class, I went ahead and did that, but then my friends talked me out of it because they're like, in real life, this is completely unrealistic. It pretty much never happens that you don't know your population mean, but you know the population standard deviation. They're related, you know what I mean? Like you use one to find the other one very often, right? They're the same kind of, they come from the same pot of data. So this is not likely, not very. So instead, we're going to use something instead of our population standard deviation. What do you think would be a good guess of what to use instead of our population standard deviation sigma? What's a good estimate for that?
25.
So that's a good guess. If it's a proportion, for sure. This is a mean. So what's my best guess for my population mean? So I want to know what the heights of all people in the country are. How would I get a good guess for the heights of all people in the country? Take a sample and find the what? This sample mean. That's my best guess for the my best guess for you is my sample mean, right? I'll write it out. Best guess for population mean mu is sample mean. So under those same ideas, my best guess for population standard deviation, sigma, is what? My sample what? Standard deviation, exactly. Sample standard deviation, S. Why? Because they're both, these guys, I'm going to use that one because they're both means, right? I use a mean to approximate a mean. I use a standard deviation to approximate a standard deviation. So, does that sort of make sense? So here, since I don't have a population mean, and you pretty much remember, well, we're going to use a sample mean S. Right? Here's the issue. Especially when the sample size is less than 30. Very often when your sample size is small, your S is going to be quite different from your sigma. It's going to be off a fair amount because small samples and how things sort of roll. Who's ever heard of Guinness Beer? Good. All right, so a lot more people than the 2 o'clock class. So Guinness Beer in the late 1800s was changing from a small brewery to a larger brewery. And there are a lot of problems with that, right? Because you go from growing your own hops and your own barley to having other people grow barley and hops for you and using theirs. And the idea with beer is you need to be consistent. Actually, any service, right? There's this great book called The E-Myth for entrepreneurs, if anyone's interested in entrepreneurs. And the idea is you need to give people a consistent service, right? So even if you give them something that's better, if it's not what they expect, they're going to be unhappy. Right? They talked about this guy who went in for a haircut, and last time he had gotten, this cold towel before, or warm towel, whatever, something like that, cold towel, and then got it. This time he did not get the cold towel. Instead, he got tea and a hair massage, whatever, other stuff, theoretically better, but he was unhappy because he was expecting the cold towel. Do you understand what I'm saying? So whenever you expect something, you have an expectation, and that's not met, then you're going to be unsatisfied. The idea of anytime you have a business, you need to be consistent. If people get something, they want the same thing each time. That's how McDonald's works. They're the same each time, right? And that's why they're successful. Even though they're not great food, it's consistent. You know what you're going to get. Okay, so same thing with beer. They need to have the beer be consistent. So what they had to do was they hired all these PhDs from Oxford and from Cambridge in PhDs in chemistry and in statistics to help them make their beer consistent. And one guy, I think his name was Robert Gossett, I'm not positive, but what he found was he had 3 samples of barley, same type of barley from 3 different farms, and he found that they're varying a lot, their variation, and then when he put them in there was not what he expected it to be. It was a lot more different than what he thought it should be, so it was throwing off all of his calculations. So what he did was he came up with a t-distribution. It's called the student t-distribution, which is It's not a z table. It's similar to a z table, but it adjusts for these small samples, so it kind of gives you a little more room for error. And in it being, this really big deal, it was a huge breakthrough in statistics, but he couldn't publish it under his own name because the beer company didn't want people to know that they had hired all these PhDs in statistics and chemistry, so he had to publish under a pseudonym called Student. So big deal, got published, but it's called the Student T distribution. I think his name was Robert Gossett, but I'm not positive. All right. Yeah, but we all know who he is now. All right, so the bottom line is, so this is all super similar. Oh, you guys all have that now. Okay, so this should look really, really similar to what we had before, right? Our confidence interval is x bar minus e to x bar plus e, right? And what we're trying to estimate, mu. We're not trying to estimate x bar. We know x bar. We're trying to guess what the population mean is. So mu goes inside of there, where my error is my critical value times the standard deviation, s over square root of n. Good? Now the difference is that my critical value is not from the z table. It's from the t table, which you all have gotten, which is based upon degrees of freedom of n minus 1. Degrees of freedom is n minus 1. We have one variable, so it's n minus 1. Let's take a look. I want to bust out that table. Get your tables out. We're going to take a look at this. All right, so you should have written down, I should be in already, critical value is s divided by square root of n, where we're using the t table with degrees of freedom n minus 1. So here's an example. Everybody have the sheet? It looks kind of like, looks like, oh, actually I have it. Forgot that. Looks like this. Yeah? Everybody has this? Looks like this. So you'll notice there's 3 rows across the top. We only care about the top row, confidence intervals. That's what we're dealing with. That top row tells you what kind of confidence interval it is. We want a 95% confidence interval, so we want the third column. Everybody on board? Third column is the one we want because that's a 95% confidence interval. Then along the side, you'll see all these degrees of freedom. So if I want, for example, sample size of 22, my n is 22. If my n is 22, what's my degrees of freedom? 21, n minus 1. Everybody on board? So the degrees of freedom is my n minus 1. So in this case, it's going to be n is 22, my degrees of freedom is 21. So everybody find your third row, your 95% confidence interval on your sheet. Find your degrees of freedom of 21. This is going to tell you what row it is. So slide it along that row until you get to the column you want. And you should have 2.080. Everybody find it? Yeah. Good? You're going to need this. This is part of what you're using for your exam next time. You need to know how to use it. Okay. Good. So what I'd like everybody to do is find the following. So what's my z-score for a 95% confidence interval? 1.96. Perfect. Now find the t-scores for a 95% confidence interval. If n is 2, again, you got to find degrees of freedom. Degrees of freedom is n minus 1. If n is 12, if n is 61, if n is 127. So everybody do that. I'll give you folks a minute or two to do that. We'll have gotten to the last one, and then they get to look at the last one. Okay, so the last one, 127. Well, let's do the first ones first. So the first one is degrees of freedom. N is 2. My degrees of freedom is what? 1. So then it's going to be 12.706. Is that right? Next one, degrees of freedom. N is 11. Degrees of freedom is 10. So it's 2.288. Is that right? 2.228. Yeah. And this one here, N is 61. Degrees of freedom is 60. 2.000. Now the last one, N is 127. My degrees of freedom is 126. What are my options? 120 and 500. Which one is it closer to? 120. So use 120. Everybody on board?
Yeah.
Okay. 1.98, yeah. All right, everybody look up. A couple of things I want you to notice. All eyes here. All eyes here. All eyes here. So what I want folks to notice is, look at my z-score, 1.96. When n is really small, it's way far away from 1.96. Because when my n is really small, my s is likely to be super far off. But as n gets bigger and bigger, my t-scores start approaching my z-score at 1.96. That's because as n gets bigger, my s gets better and better, closer to sigma. So I need to take less of a room for error. Does that make sense? So you'll notice kind of that's what's happening. That's what's happening. Okay. There are some characteristics of them. Variance is larger than 1. The t-distribution is actually a family of curves, one for each degree of freedom. And as we talked about earlier, as your sample size gets bigger, t gets closer and closer to z. So here are actually some curves themselves. You can see, they're kind of more flat when you have a small sample, but as your n gets larger, it gets closer and closer to z there. All right, problem 7 on lab. Do problem 7 on lab. Find the t-value for n is 18 for a 99% confidence interval. Do it.